chromatic dispersion, it is also called as intermodal dispersion. So it may occur in all types of optical fibers as a result of the finite spectral line width of the optical source, which does not emit spectral line width of single frequency but a band of frequencies. So this is the first type of dispersion. So when you classify dispersion, we have two categories. One is the intramodal dispersion and other one is the intermodal dispersion. Intramodal dispersion is because the dispersion that is exhibited by a single mode or the mode itself. The dispersion caused by a mode is what we call it as intramodal dispersion. So let me study in detail. Let me study in detail of what causes the intramodal dispersion uh, in the coming slides. But comparison of intramodal with that of intermodal dispersion is because the dispersion caused between any two modes, or the dispersion caused by multiple modes. So one can make uh, sure that intramodal dispersion, it happens within the mode, and intermodal dispersion is because of different modes or multiple modes. Okay. So let me take up the first kind of dispersion, that is intramodal dispersion. So intramodal dispersion is also called as chromatic dispersion. And what are the causes of this intramodal or chromatic dispersion? It may occur in all types of optical fibers as a result of finite spectral line width of the optical source, which does not emit just the single frequency but a band of frequency. If you can take an optical source, say laser or an LED, laser or an LED. So they are going to emit the light from their sources, but not of single frequency, but a band of frequencies. So this band of frequencies will contribute to different spectral components. So different spectral components. These spectral components are not propagating inside the fiber at the same velocity. They are going to propagate at different velocities, so which causes our intramodal dispersion. So you can see here there may be a propagation delay differences between the different spectral components of the transmitted signal. This causes the broadening of each transmitted mode and hence appears intramodal dispersion. The delay differences may be caused by the dispersive properties of the waveguide material. In that case, we call it as material dispersion, or this delay differences between the different spectral components can be caused due to the guidance effects within the fiber structure. In that case, we call it as waveguide dispersion. So in intramodal dispersion, we have two classifications again. One is material dispersion, in which the delay differences between the spectral components of the light emitted by an optical source, uh, if it is caused due to the waveguide material, it is called as material dispersion, or if it is caused due to the guidance effects in the fiber structure, it is called as waveguide dispersion.
So I can't hear anything.
Sir, we can't hear you, sir.
So pulse broadening due to material dispersion, it results from the different group velocities of various spectral components that are launched into the fiber by the optical source. So optical source such as laser or LED is going to launch the light into the fiber, and that light is constituted it is constituted of different spectral components, and all these spectral components are not traveling with the same velocity instead with a different group velocities. So because of which the pulse gets broadened, and that we call it as material dispersion. So let me take this statement. A material is said to exhibit material dispersion when the second differential of refractive index with respect to wavelength is non-zero. That is, d square n divided by d lambda square is not zero. So why we need to consider this statement? Because uh, you can just read the previous one. uh, Material dispersion occurs when there is phase velocity of a plane wave propagating in a dielectric medium varies non-linearly with wavelength. So this phase velocity of a plane wave which is propagating in a dielectric medium, that phase velocity, it varies non-linearly with wavelength. So that is the reason why we need to consider the wavelength as one parameter. And because the phase velocity is related to refractive index, we need to consider refractive index as another parameter. So in this statement, the second differential of refractive index, that is n, small n, with respect to wavelength is a non-zero. If it is equal to zero, then there is no existence of material dispersion. But it cannot be equal to zero because some amount of material dispersion is exhibited by the fiber material itself. So it's a non-zero quantity. The pulse spread or pulse broadening due to material dispersion may be obtained by considering the group delay. So we need to consider another parameter called as tau g, which is group delay in the fiber, which is reciprocal of group velocity. So group velocity is inversely proportional to group delay. So we are going to consider the group delay expression now. Tau of xg is 1 by c n1 minus lambda dn1 by d lambda. So this is a equation one has to consider in order to proceed with the derivation. Okay. So n1 is nothing but the refractive index of the core. So pulse delay tau m due to material dispersion in the fiber of length L. So this is without considering length as a parameter. So tau m, when tau pulse delay with respect to length of the fiber is will represent it as tau m. So pulse delay without group delay expression is given by tau of xg, which is 1 by c n1 minus lambda dn1 by d lambda. That is group delay expression, which is inversely proportional to group velocity. So pulse delay, because the pulse travels inside the fiber of certain length, so we may change the expression of group delay to pulse delay as tau sub xm, which is equal to L divided by C n1 minus lambda dn1 by d lambda. So this is the expression for pulse delay after it traverses a distance of length L. Coming back to the source concept, that is, we can have a laser source or an LED source, both of which will emit light as an output. So for a source, an optical source, which is having an RMS spectral width, which is represented by sigma sub x lambda. Spectral width is nothing but the width of the light that is emitted from the optical source, which we call it as RMS spectral width. That is represented by sigma sub x lambda, and the mean wavelength, the wavelength in which the source is emitting the light, is called as lambda. RMS pulse broadening due to material dispersion can be given by sigma m. Sigma sub x m is the representation for our RMS pulse broadening due to material dispersion. And how do we relate that to the pulse, the spectral width and the wavelength? This is how the expression goes. So we have some relationships between uh, material dispersion and spectral width, as well as wavelength and pulse delay. So sigma m is equal to sigma sub x lambda d tau m by d lambda, differentiation of pulse delay with respect to wavelength. So pulse spreading may be evaluated by considering the dependency of pulse delay on lambda. So let me differentiate the previous expression. This is the expression of pulse delay d tau m by d lambda. Differentiate that with respect to lambda. What you will be obtaining is L by C lambda. You do the normal differentiation with respect to lambda, so that some of the terms get cancelled. So d tau m by d lambda is minus L by C lambda d square n1 by d lambda square. All right. So this is the term that we obtain for d tau m by d lambda. So replace that term in the previous expression of sigma m. Sigma m is approximately equal to sigma lambda. D tau m by d lambda is minus L by C lambda into d square n1 by d lambda square. So replace that. So if you want to ignore the negative sign, you can take magnitude for lambda into d square n1 by d lambda square, so that the negative sign can be eliminated. So this is the expression for the material dispersion, considering length, refractive index, and wavelength, along with the spectral width of the light source. So one has to define a parameter from the same expression. We are going to define a parameter called as material dispersion parameter, represented as capital M. Capital M represents the material dispersion parameter, and its value is equal to lambda into d square n1 by d lambda square, or it is lambda square d square n1 by d lambda square. Either you can use these two terms to represent material dispersion parameter, and the unit of that is represented in picoseconds per nanometer per kilometer. This is the standard unit for the material dispersion parameter, capital M. M is lambda by C d square n1 by d lambda square. So please remember this equation. M can be represented either in terms of lambda d square n1 by d lambda square divided by C, or it can be lambda square. That we will come to know once we do the problem. Okay. So M is now lambda by C d square n1 by d lambda square. So consider this quantity in this sigma M expression. So you can find lambda by C into d square n1 by d lambda square. Okay. So this part is now represented as capital M. So what happens to sigma M now? Sigma M will be sigma lambda into M into L. So you can see sigma M is sigma lambda into M into L. Okay, what is M? M is lambda by C d square n1 by d lambda square. And the unit of that is picoseconds per nanometer per kilometer. So please remember that expression, because we have a problem to solve related to material dispersion, which is an important question in the exam. So let me take the statement now. Okay. A glass fiber exhibits material dispersion, which is given in terms of lambda square, magnitude of lambda square d square n1 by d lambda square, which is of 0.025. Determine the material dispersion parameter, that is capital M, as wavelength at a wavelength of 0.85 micrometer, and estimate the RMS pulse broadening per kilometer for a good LED source with an RMS spectral width of 20 nanometer at this wavelength. So first thing which we have to estimate here is material dispersion parameter, that is capital M. So what was the expression for capital M that we took? Lambda by C magnitude of d square n1 by d lambda square. So this is the original term of capital M that we took, but in the statement, in the problem statement, they have defined lambda square into d square n1 by d lambda square as 0.025 material dispersion related to lambda square d square n1 by d lambda square is 0.025. So let me rearrange this expression in terms of lambda square d square n1 by d lambda square. So you have to rearrange the m expression in terms of the given expression lambda square d square n1 by d lambda square. So you just multiply and divide the expression by lambda so that it gets rearranged as 1 by c lambda into lambda square d square n1 by d lambda square. And this term is given as 0.025. You can substitute that 0.025 divided by c. C is the velocity of light in free space, and lambda is whatever the value that they have mentioned as 0.85 micrometer. And one has to remember that capital M unit is picoseconds per nanometer per kilometer. So please understand the M should have the value only in terms of that unit, picoseconds per nanometer per kilometer. So one has to take the terms in the expression, substitute the terms in the expression in such a way that the unit turns out to be picoseconds per nanometer per kilometer. So numerator is 0.025, what is given here in the statement. Denominator C is 3 into 10 power 8 meters per second. But here, since we need in terms of kilometer, I'm changing the value of C as 3 into 10 power 5 kilometer per second. Okay, and wavelength they have given in terms of micrometer, that is 0.85 micrometer, but we have the unit in terms of nanometer, so change it to 850 nanometer. Okay, so 0.025 divided by 3 into 10 power 5 into 850 seconds per nanometer per kilometer, that is the unit. So once you do the calculation, it turns out to be 98.1 picoseconds per nanometer per kilometer. So this is the M value, that is material dispersion value in standard unit, picoseconds per nanometer per kilometer. So let me continue with calculation of RMS pulse broadening sigma suffix M due to material dispersion. So what is the expression for that? Expression for that is RMS pulse broadening is given by sigma suffix M, which is approximately equal to sigma lambda divided into L divided by C, magnitude of lambda into d square n1 by d lambda square. But we have the other expression, how it the RMS pulse broadening is related to material dispersion parameter capital M, length of the fiber L, and spectral width sigma lambda. So let me take this example expression because we already have the value of capital M. Okay, so M is 98.1 picoseconds per nanometer per kilometer. L is the length of the fiber, and we will be taking as 1 kilometer here for the substitution purpose. Sigma lambda is 20 nanometer as it is mentioned in the problem statement. So RMS pulse broadening per kilometer due to material dispersion now for 1 kilometer is sigma is 20 nanometer. You substitute as 20. L is kilometer, you substitute as 1. 98.1 into 10 power minus 12, that is capital M, because all the other terms like 20 nanometer will get cancelled with per nanometer of the unit of capital M, and kilometer 1 kilometer gets cancelled with per kilometer for capital M. Okay, so RMS pulse broadening for material dispersion parameter is given by 1.96 nanoseconds per kilometer. Okay, so this is the RMS pulse broadening material dispersion. So looking into this plot of material dispersion parameter,